Alright, this is part 3 of convergence testing series. We're testing convergence of infinite series, and we explored a couple of tests: the divergence test, limit comparison test, and, comparison test, limit comparison test, and integral test. In the integral test, we learned about the p-series and when it diverges and when it converges. So thanks to the integral test, we know that if p is less than -1, we have convergence and divergence for any other value of p. And the p-series, though, can be written in an equivalent fashion, 1 over k to the p, and that changes our boundaries. It converges when p is greater than 1 and diverges for all else. But we can use these p-series. They're really handy for use in comparison testing. So anytime a p-series emerges, in a comparison, we can use our understanding of the convergence of p-series to make it more efficient. So earlier we looked at this particular series where we have a linear divided by a quartic polynomial, and we made a comparison to 1 over k cubed. Now that we know 1 over k cubed is an example of convergent p-series, we can use that as our argument for comparison. So the comparison test does in fact prove convergence because I know the convergence of 1 over k to the 3. So this is a great example in terms of application of TOK concepts and principles of use of prior knowledge to help us with our current situation. But moreover, how many different tests are related into proving convergence and how all the different elements of logic all pile together. Anyway, I digress. This is then a p-series, and when p is -1, we actually have a special name for that p-series. It's called a harmonic series. Another form of the harmonic series is 1 over k instead of k to the -1. Now, what happens if I take -1 to the k plus 1 power? You'll see where this goes. But when I take 1 over -1 to the k plus 1 power, I observe that we alternate back and forth between -1 and +1. Plus, minus, plus, minus, plus, and that should continue. All of the odd values of k are going to produce positive numbers and negative numbers for all the evens. Now if I change this from k plus 1 to just k, then the odd numbers are going to have the negative ones and the even exponents are going to have the positive. So what? Well, you will often see series that have -1 to the k plus 1 times some other part. That creates an alternating series. Here's an example of an alternating series. This is specifically an alternating harmonic series. So, by the way, you might see the cosine used to create alternating series because we know that the cosine of 0 is 1, the cosine of pi is -1, the cosine of 2 pi is 1 again. So we can alternate between 1 and -1 depending on how skillfully we apply the cosine function. So be aware of that. If you ever do see a cosine in a series, think that it might be what's causing alternation, or at least it's going to cause changes between positivity and negativity. So I know that the harmonic series does in fact diverge. But what about if I do an alternating harmonic series, because I'm actually subtracting some of the values to the total sum? So will that subtraction be enough to create convergence? In order to explore that, we need to develop a new test, explore a new test, and that's called an alternating series test. The alternating series test is really handy, and it's quite significant. So for any alternating series at all we have to do is prove that the sequence decreases for sufficiently large values of k, and that the limit of the absolute value of the sequence is 0. That's enough to prove that we have convergence in our series. I just want to explore this for a second. First of all, what we're showing here is the next consecutive term, absolute value-wise, will always be less than the term before it. It says for sufficiently large k. Usually this would be true for all k, but what this particular theorem is doing is accounting for situations where perhaps u sub k plus 1 is greater than u sub k in the beginning, but at one point they eventually cross paths, and then this is eventually going to be true. We can just show that for sufficiently large values of k, this is true. That's enough to qualify for alternating series test. So all we have to do is take the absolute value of the sequence, and if the sequence approaches 0, then the series will converge as long as it's a decreasing positive sequence. So let's look at our alternating harmonic series. The absolute value of this sequence is 1 over k, because the absolute value negates any negativity that will emerge from this little trick. So I know that 1 over k plus 1 is always going to be less than 1 over k for any positive values of k. And I also know that the limit approaches 0, and therefore by the alternating series test, this particular harmonic alternating series does converge, which is interesting because the series 1 over k, the harmonic series, is divergent, but the alternating series is convergent. That concludes the video. Well, that's about all I got. I should have made the last one shorter and this one longer, but so be it. More to come soon.